Thank you, Lucas, for introducing the insurance application of image recognition. Now, I'm going to talk about the challenges to applying image recognition to insurance and how image data can be pre-processed before being used for recognition tasks. First of all, although the accuracy of image recognition techniques is continually improving, errors are inevitable. Indeed, the accuracy level of applying image recognition techniques to the insurance industry is a key obstacle. Currently, the highest accuracy rates for popular image recognition competitions, such as the ImageNet Large-Scale Visual Recognition Challenge, are usually between 70% and 90%. This is unlikely to be good enough for many insurance applications. Even with the most advanced image recognition models, false conclusions are not unusual. For example, different family members may be recognized as the same person and log into the same cell phone using facial recognition. This may be a problem if the primary user's insurance account information is protected by facial recognition. A small error can lead to customer complaints and financial losses. For example, if a cancer patient applies for a life or health insurance, and a CT image of the tumor is used to predict the risk and determine an appropriate charge, an error in the image recognition model estimation could lead to unnecessarily higher premium or even rejection of the insurance application. The second challenge is that the collection of data and model training may take a long time and require many resources. The existing models are usually trained to identify the objects in an image. However, for insurance applications, more useful information may be the behavior of the object. For example, is a house roof in good enough condition to withstand hurricanes? How many insured houses were hit by a tornado? This often leads to more customized model training using relevant image data. Fine-tuning the model with specific training data is necessary to improve the accuracy for insurance applications. Yet, these steps may be time-consuming, and many resources have to be allocated, from data collection to feature extraction and classification. Next, let's move on to data processing. Given an image, a model's first task is to transform that image into a format which computers can understand. You've probably known that an image is composed of pixels, the smallest particle in digital imaging. Each pixel can be described by its color. In the most popular color imaging system, the RGB system, a color can be represented by a three-element vector, which includes scales of how strong each primary color, red, green, and blue is. Thus, any image can be transformed into a matrix of RGB vectors, with each vector describing a pixel of the image. Here shows how a green cross can be transformed into a 3 by 3 matrix. There are 9 pixels in this image. Each one of these pixels is either in white or green, so we convert it into a RGB vector and get this matrix. Sometimes images may be altered for different purposes. For example, to save up computing capacity, images may be compressed to a lower resolution or converted to grayscale, where each pixel is represented by a weighted average of the RGB values. This reduces the data volume of the image by 2/3 and saves up much space complexity of data storage. In addition to grayscale transformation, we may augment the images before feeding them into an image recognition model. Common augmentations include flipping, rotating, shifting, cropping, and brightening. Usually, augmentation is either used to provide additional training examples or to increase the robustness of the image recognition program. If a model is robust, it should be able to generate the same conclusion no matter from what angle the image is taken. This concludes the data processing of applying image recognition to insurance. We invite Richard to give a presentation on the recognition model itself.